Hi, today I'm going to do the introduction to the Wittgenstein presentation on moving from FreeRTOS to SAFERTOS. I'm going to start by talking a little bit about what FreeRTOS is to make sure everybody understands that before handing over to Steve Ridley from Wittgenstein, who is going to take the main presentation about moving to SAFERTOS. So starting then with what FreeRTOS is, I mean, it's fairly easy to describe what it is because the name is very descriptive. It is a free real-time operating system, or FreeRTOS with the acronym. The FreeRTOS package actually comes with a whole set of libraries, including a TCP/IP stack. Today we're mainly talking about the kernel. The kernel is a C library. Effectively, it's a C library that implements multi-threading. So you build that C library into your application, and that gives you the ability to use the API and then design your application as a set of autonomous but communicating tasks. I use the term tasks and threads a little bit interchangeably, I'm afraid. When I do that, really I am talking about the same thing. Now, FreeRTOS has been ported to something like 40 different architectures and 20 odd different compilers. It's worth noting that it also runs in Windows and Linux. You won't get real-time behavior if you run it in Windows and Linux, but those environments do give you a very feature-rich debugging environment. They're useful for doing things like unit tests or developing code which doesn't require the real hardware. In fact, we've done most of our TCP/IP stack development inside the Windows port. Outside of those non-real-time environments, though, on the screen now I'm trying to show the kind of sweet spot for the microcontrollers, the 40 microcontroller architectures that FreeRTOS runs on. Steve's probably seen this diagram 1,000 times before. The blue line here is the blue box here is trying to show where FreeRTOS is applicable. So the higher up the y-axis that blue line is, the more applicable FreeRTOS is. The further along the x-axis you go, the more powerful the processor you have. So on the left-hand side, that orange is trying to show there's, very small. You're probably not even going to be using C, to be honest, let alone a scheduler. As you move along the x-axis, where that blue starts going up is where FreeRTOS starts to become applicable, maybe in the 8-bit space. But where the blue is kind of crossing the orange, this is where you're more likely to get benefit from using multi-threading than not. And this is in the kind of Cortex-M0 to Cortex-M7 space. If you go to the far right-hand side, we've got low-end Cortex-A. And then if we go way, way off the scale, you're into the kind of 64-bit space. That's I haven't bothered showing that on the screen because that's not really the primary kind of use case for FreeRTOS. Moving on to the next slide then. This is showing the kind of growth of FreeRTOS over the years. The number of downloads is one of the things we can count. Last year, it was averaged about once every 175 seconds. This is actually a huge undercounting because these are just people that download the code from us. You can actually get the FreeRTOS code from lots of different places. You can see at the end there where the blue kind of turns into a darker blue or black line, that's when we move to Git or GitHub. Prior to that, FreeRTOS was in SourceForge, so these numbers come from SourceForge. Now, as FreeRTOS grows, the ecosystem grows, becomes a kind of virtuous circle, and Wittgenstein have been a very important part of that ecosystem for a number of years with OpenRTOS, which is a commercially licensed version of FreeRTOS, and also SAFERTOS, which is what Steve is going to talk about today. Moving on, this also shows growth. It's just unique visitors to the freertos.org website. However, Google counts a unique visitor. You can see there's fairly steady growth there as well. So the next few slides then are going to take us through some of the more recent developments that we've done with FreeRTOS. I've spoken already a little bit about the kernel moving, actually the whole FreeRTOS package moving into Git. That's been hugely successful. I wish we'd done it earlier. You can go to the FreeRTOS, was it github.com/FreeRTOS, and see all the activity there. We've got contributions from 5 or 6 or 7 different silicon vendors now. It's been great. The other thing we've done is move the forums, because you can get FreeRTOS from lots of different places. We've moved the forums directly onto the freertos.org site. That also has been very successful, and it's important to note that here you can get access to the FreeRTOS developers, so you can get support directly from the people who are writing and contributing to FreeRTOS, and that's also been greatly successful. You can get a lot of confidence just by going and looking there. So next, a few slides just talking a little bit about some of the kernel development work. This is going back maybe a year or so. This is showing some of the work we did for a kind of low-level efficient transport mechanism for core-to-core communication. The next slide here is showing some of the work we've done on ARM-V8M. We've had an ARM-V8M port. This is Cortex-M23 and 33 for a while now. In the last few months and years, we've actually got a growing number of people taking actual products to market now on this, and they're giving us some great feedback, and we're using that feedback to improve the port. I actually did a talk yesterday on using FreeRTOS on Cortex-M with some of the ARM's platform security architecture as well. It's a very, very flexible port. You can build in trust zone, you can run the kernel on the secure or non-secure side, etc. This final, that was a screenshot of a blog post on the freertos.org site telling you how to do that. This is a screenshot that shows some of the configurations in GitHub. Here we've most recently introduced an improvement to the direct-to-task notifications. This is a very efficient way of interrupts communicating with tasks or tasks communicating with tasks, originally designed for driver libraries, so a task could wait for an event from an interrupt. Moving on then, I want to preempt some of the questions that we inevitably get about Amazon's involvement in FreeRTOS now. And actually, I would like to thank Amazon on behalf of the whole community for their very unselfish investments in FreeRTOS, because whilst Amazon naturally have an interest in making sure that the many FreeRTOS people that connect to their IoT services, so this is Amazon Web Services IoT specific services, now, there's obviously an interest in making sure that people can connect as securely and as quickly as possible. All the investment is being released as open source MIT code. So this can be used for any purpose. A lot of FreeRTOS applications, if not the majority, don't connect to anything. Many connect to AWS, but other cloud services as well. And this is the value that Amazon bring to the whole community. Some of the things which may be less obvious because they're not kind of in the documentation are things like the security expertise. I'm showing a couple of images here actually from another blog post on the freertos.org site that shows how Amazon are using their expertise to do things like memory safety and thread safety proofs on the code, which is fantastic. Also, especially specific to IoT, Amazon have a lot of expertise and practiced processes for dealing with things like investigating potential security threats, mitigating those threats, rolling out patches and that kind of thing. So that now all applies to the FreeRTOS code as well. And remember, this is MIT licensed code that you can use for anything. So swiftly moving on, because I want to get to Steve, I'm going to talk a little bit about what we are up to now. This slide here is showing some of the work we are doing to actually take a lot of that value that Amazon are adding, I've just been talking about, and moving it directly into the main FreeRTOS distributions. If you go to the AWS GitHub rather than the FreeRTOS one, you will find these reference integrations. These are fully tested, fully integrated, and ported and tested platform-specific projects which provide everything you need just to connect, all the security and connectivity and secrets management and provisioning, over-the-air updates, all these things that you just need to be able to have an internet-connected product. They're provided as fully integrated references so that you can just focus on adding value. But a lot of that, a lot of the libraries in those integrations are not Amazon specific. So things like MQTT, a protocol often used in IoT, HTTP, PKCS is like the kind of global standard for accessing crypto objects, that kind of thing. We've done a lot of refactoring work, split those out so they can be used by themselves. In fact, if I move on to the next slide here, you can see that things like MQTT, we've refactored those so that they are the base functionality. They're completely independent now from even multi-threading, let alone FreeRTOS. The only thing they're dependent on is the C library. And we've brought those into the FreeRTOS Git repo, and the way you can use these now is across a whole spectrum. So if you have, there's no even dependency on the TCP stack. So if you have an application which is already developed using whatever TCP/IP stack, maybe it's not even using multi-threading, it's on an 8 or 16-bit device, you can bring that library in and use it. That's at one extreme. The other extreme I've just mentioned, which are these complete reference integrations. And then in the middle, you have the more traditional FreeRTOS mechanism, where we can run these libraries inside tasks. So the task is what we call a daemon or agent, and that is going to manage all the sequencing and all the timing and the retries for the protocol for you, and gives you just a very, very simple interface. All that is running in the background for you. So we can see we can kind of cover that whole spectrum. So that was it. That was a very, very quick introduction to what FreeRTOS is, a little bit of the history, a lot about the value that the ecosystem, particularly like Wittgenstein and Amazon, are bringing, and what you can see happening in Git at the moment. And with that, I am going to hand over to Stephen, who is now going to talk about how you can move your FreeRTOS application into SAFERTOS. Thanks.
Thanks, Richard, for that overview of FreeRTOS. Hello, everyone. My name is Steve Ridley, and I lead the engineering team here at Wittgenstein High Integrity Systems. We're the people who are responsible for SAFERTOS. Now, the virtues of FreeRTOS are obvious. It's widely deployed, trusted, supports a massive range of platforms, and of course, as the name tells us, free. However, when we're developing for the safety critical market, we need more. We need the ability to prove correct operation of every part of this system in accordance with the various industry-specific safety standards. This is where SAFERTOS comes in. So today I'm going to briefly explain what we mean by safety critical. Then I'll explain why SAFERTOS might still be your initial development platform, even if the design is ultimately part of a safety system. And finally, I will touch on issues of migrating from free to safe. So first, what do we mean by safety critical software? It's software with some kind of executive role in a safety critical system, which is broadly something that might cause harm, death, or have other grave consequences should it go wrong. Different industry sectors, aerospace, automotive, medical, rail, all have their own safety standards that set out development and coding practices that must be followed. Ultimately, the aim is to classify, eliminate, or mitigate risk. And risk classification is usually referred to as safety integrity level, or SIL, as you'll probably hear me referring to it through the rest of this talk. In a safety critical system, we're not just talking about code or coding practices. There must be a clear tracing of requirements through design, implementation, and testing. We need to prove that the code does everything it should as safely as possible and does nothing extra or unexpected. Some of the things shown on this slide are gleaned from safety standards, others come from device-specific safety manuals, but they all help to create and strengthen a safety argument. For example, clear should be simple and clear and written to accepted standards. It's easier to verify and maintain. It's not rocket science. Everything should be made more as deterministic as it should be. A deterministic system is much easier to test and characterize. Memory should be statically allocated. The potential problems with heaps have been widely documented for many years. Buffers should, where practically possible, not be repurposed after use. We should be doing integrity checks on key data periodically or when used. Peripheral control registers and the like should be read back to check that they were written properly. Remember, when developing for a safety system, it's all about mitigating and eliminating risk. The more we can do by adopting good development practices, the better. So, IEC 61508 is the most widely applicable standard for safety critical systems. And it not only sets out the quantitative basis for these SIL levels and the modes of operation and so on, but covers the whole life cycle of safety functions. To meet this standard, a safety function has to be designed, developed, and deployed with well-audited rigor. Other standards exist that are tailored to specific industrial areas. We have 26262 that's applicable to automotive systems. In the railway world, Senelec produced their 126, 128, and 129 standards. Aerospace has DO178, 254 and SAE standards and so on. They all have some broadly analogous notion of safety levels, that though the names differ and they're not really directly comparable. Safety certifying software is hard because, as we all know, there's so much that can go wrong. The more complicated the software, the harder it is to be confident that there's no errors, or even that you've accounted for and mitigated all the ways in which you think it's possible for it to fail. It's all about managing risk. So, what is SAFERTOS? Well, back in the mists of time, Richard Barry was working for a small British aerospace and simulation business, which itself was part of the Wittgenstein Group. And local legend has it that he spent his evenings sitting in his bedroom developing FreeRTOS. However, he and others at Wittgenstein soon realized that there was a real demand for something like FreeRTOS that was tailored to the safety critical market. Wittgenstein High Integrity Systems was formed to develop SAFERTOS, and SAFERTOS is based on the FreeRTOS functional model that has been completely re-engineered to be safety certifiable in accordance with the major industry safety standards. So today, SAFERTOS is offered pre-certified for a given platform and compiler, which typically saves customers time, effort, and money attempting to validate and certify what is a fairly major and complicated component of the final product. Using SAFERTOS brings the benefits of a tried and tested RTOS, but without the overhead of validating and certifying third-party code. SAFERTOS deliberately and unapologetically follows the FreeRTOS functional model. We acknowledge its huge popularity and widespread use, and the fact that it can offer a relatively easy migration path for developers with a FreeRTOS background. So it might sound odd, but we actively encourage people to prototype with FreeRTOS. For one, it's free. Two, nearly all the semiconductor manufacturers provide example programs for their processors, and nearly all of them base those example programs with FreeRTOS-based examples. It means that there's a very low barrier to entry at the project outset. And if the ultimate goal is a safety product, then migration to SAFERTOS is easy. Though it is worth pointing out at this point that there's more to a safety product than just the RTOS. The entire application does have to be developed with the rigor required by the SIL level of the applicable safety standard. Having a safety RTOS is just one step along the way. So, in spite of sharing a functional model with FreeRTOS, there are things to think about when migrating from free to safe. The main thing to consider is memory allocation. SAFERTOS doesn't use any dynamic memory allocation, and therefore all memory buffers all task stacks are the responsibility of the application developer. Nothing is created for you behind the scenes. It's the same with the task control blocks, queue buffers, etc. You, the application developer, need to develop the buffers, to allocate the buffers and provide them to SAFERTOS. Where supported by the processor hardware, SAFERTOS will make use of the memory protection unit. To make maximum use of this feature, the application designer needs to understand his memory map, which variables are needed to be seen by which tasks, which peripherals need access from which tasks, etc. And grant those privileges. The API we have differs slightly from free to safe in that some functions have slightly different names. Some functions will take different parameters, and FreeRTOS has a full set of error codes, which we encourage people in a safety application to religiously check. The picture on the right-hand side of the slide is the cover page from our migration guide, which is available as a free download from our website. Generally, though, converting the application code from FreeRTOS to SAFERTOS is a straightforward process. The application code remains the same, and it is possible to perform the porting exercise in a controlled and deterministic manner. However, another way of migrating from FreeRTOS to SAFERTOS is to do the absolute minimum and use a wrapper layer between your application and the RTOS. Many of our customers do exactly this. as it allows them to readily switch between free and safe across their company and their range of product. It also permits the organization to control the subset of features that the app developers are permitted to use. Another thing to consider is existing library code. We've heard Richard talk a lot about the AWS TCP/IP stack, and at least when I last used it, it did natively use and rely on FreeRTOS primitives. And while, of course, it is possible to convert library code so that it uses the SAFERTOS API and maintain that branch, it's not ideal. And it is generally more convenient to use a wrapper layer to convert SAFERTOS calls back to FreeRTOS. So the shared functional model makes it relatively easy for us to develop and implement wrapper layers that can work in both directions, i.e. free to safe or safe to free. So up to now, I've talked about how similar FreeRTOS and SAFERTOS are. Now it's time to focus on the differences. So firstly, when compared with FreeRTOS, SAFERTOS is minimal or more minimal. It doesn't necessarily mean a smaller footprint. The extra checking and integrated MPU support do have some cost. However, the advanced feature set is somewhat different. SAFERTOS is focused on safety and is supplied with a design assurance pack, or DAP, that provides the evidence to back the safety claims. And we work with TÜV in Germany, and SAFERTOS is pre-certified to both IEC 61508 SIL 3 and ISO 26262 ASIL D. So let's compare some features. First, the MPU. FreeRTOS does have some MPU aware ports, but there are a few, and the way the MPU is used differs quite markedly. In FreeRTOS, the MPU is to a certain extent an add-on, so that you create the tasks as usual, but then choose to make some tasks restricted. That is, you can make them run in an unprivileged mode so that they can be denied access to kernel data and so on. With SAFERTOS, on the other hand, the MPU is generally considered an integrated part of the offering, and it's a fundamental part of the RTOS. All tasks are created from the outset as either privileged or unprivileged. All tasks have a set of MPU parameters that can grant any necessary additional access to unprivileged tasks. SAFERTOS ports do exist for non-MPU processors, but these days they are a rarity. So next, static allocation. In FreeRTOS, the kernel uses some kind of heap function, malloc in Unix terms, to allocate memory for task stacks, queue buffers, and so on from a memory heap. In fact, FreeRTOS provides, I believe, 5 of these heap management schemes to choose from, whereas in safety-critical software, we prefer to statically allocate everything. So SAFERTOS has no heap functions and does no automatic memory allocation. It is important to say that we don't say that our application can't use dynamic memory allocations. It's just that FreeRTOS also has options for how the scheduler works and can be quite comprehensively tailored by conditionally compiling different functionality in or out. These don't really fit either with a safety critical certification. We want to certify a fixed configuration, and we're looking to reduce the number of things that might change. If there were just 2 optional features, suddenly we'd have 4 possible builds to thoroughly test and validate. So with SAFERTOS, we have a single set of features. In FreeRTOS, there are macros throughout the kernel that can be used to track kernel activity, like switching in and out of tasks or deletion of queues and so on. In SAFERTOS, we can't generally allow application code to be built into the kernel, and we still retain the credit for our validation and certification. So we don't have any of those. And there are also some other features and facilities that we consider not strictly necessary. So the API is leaner, and SAFERTOS is much slower to introduce new features, as the safety case for each has to be meticulously built. So SAFERTOS looks more like this. Some things that are difficult to fit into the safety critical software paradigm have been removed. The MPU takes a much more central role in most ports, and we have a leaner and meaner API overall. Yeah, okay. So for those that are still awake, this slide is a duplicate of the one I showed earlier. However, it summarizes the main issues to consider when porting from FreeRTOS to SAFERTOS. Firstly, memory allocation. SAFERTOS doesn't use dynamic memory allocation, and therefore all memory is allocated by the application and fixed for the lifetime. Understand your memory map. Second, use of the MPU. To make maximum use of this feature, the application designer needs to understand what variables, peripherals, etc. a task needs access to. There are modes that require less involvement in memory partitioning, but the benefits of the feature are then very much reduced. There are some differences in the API. Some fictions have different names, etc. But overall, these can be readily taken care of by following the FreeRTOS to SAFERTOS porting guide. So overall then, SAFERTOS is a safety-focused upgrade from FreeRTOS, and although its API is generally a little less rich, it offers enhanced MPU support and is developed and maintained to rigorous accepted safety standards and offered as a pre-certified platform on which to build a safety-critical product. And so thank you, Richard, for taking the time to provide the introduction for this talk. And thank you, everyone, for listening.